So I would like to start my presentation with this video. You can see this is the 3D printing technology that we have used to create a smart structure. This is 4D printed box that can be closed by itself when it exposed to water. And you can see this is a scorpion, and you can see the legs are going down and the tail is going upside, and the hands are moving sideways. This is 4D printed flower that can change its shape over time. This is the 3D printing process of shape-memory-hydrogel material. This is one type of composition. And this one is another type of composition. This is 4D printed flower using shape memory materials. And I have made this 4D printed gripper using shape memory material that can hold an object and also can transport an object underwater and also in air. And as this material has shape memory property, so it can release the object underwater. In this talk, I will particularly focus on shape memory hydrogel materials, which has amorphous state and this crystalline state. And the shape of this material can be recovered, followed by heating and cooling. And I have synthesized this material using two different monomers. One is N,N-dimethyl acrylamide, which is amorphous in nature, and another one is sterile acrylate, which is crystalline. And you can see this is the initial state of the shape memory material. And if you increase the temperature above 40 degrees Celsius, that means the above the glass transition temperature of this material, the crystal molecules melts, and you can extend or stretch or twist whatever you like. You can do with this material. And if you decrease the material lower than 40 degrees Celsius, then the crystal reforms again and you will get the temporary shape. And if you give heat again, you will get this recovered state. Here is the fabrication process of a shape memory material. At first, we make the pizzle solution by mixing all the monomers, crosslinkers, initiators, EV absorbers, and stir it for 10 to 15 minutes with continuous supply of nitrogen bubbling. And then we use this pizzle solution for 3D printing. This is stereolithography. And for this 3D printing process, we have used this 3D printer. We call it Swimmer. And using this 3D printer, we have made these models like this finger shape and hollow cube shape. For 4D printing of these shape memory hydrogel materials, I have chosen two different composition. You can see this is a SMG 70 SA30, which represents 70% of damam concentration and 30% of SA concentration, that means sterile acrylate concentration. And another one is SMG 90 SA10, where damam concentration is 90%, SA concentration is 10%. And here is the image of 3D printable shape memory material. And this is the 4D printing of the flower, 4D printed flower. First, I have printed the first layer and then changed the solution and then print the second layer. Here is the dynamic mechanical analysis data of this material. And we have found that both layers or both composition has an excellent shape fixity and recovery ratio. And you can see here for all cycles, the shape fixity ratio is above 99% for all the layers, and for recovery ratio for the first cycle is around 85, above than 85%, and for from the cycle 2, the recovery ratio is above than 99%. This difference, we call it training phenomena here. And to make this bilayer, I have chosen this SMG 90 SA10 as a outer layer, which has higher amorphous concentration, monomer concentration, and the inner layer made of SMG 70 SA30, which has higher crystalline concentration, crystalline monomer concentration. And when the bilayer is exposed to water, the outer layer absorbs water and trying to expand, and that's why it creates some stress in the mid plane, and that's why the bending is happened. And here is the illustration of the bilayer of coil formation, full coil formation. And we also have found the partial recovery in hot water and full recovery in air when heat is given. Here is the mechanical properties of SMGs, and I have examined the printing angle dependent tensile test, and this portion represents SMG 70 SA30, where the crystalline concentration is higher, and it shows somewhat rigidity. And this portion is for SMG 90 SA10, where the amorphous concentration is higher, and it shows somewhat flexibility. And we didn't find any change in mechanical strain for changing of printing angle from 0 degree to 90 degree. And we have found interesting data for temperature dependent tensile test method, and we have found that this dotted line represents the SMG 90 SA10, where the amorphous concentration is higher. There is no significant change. And for SMG 70 and SA30, where the crystalline concentration is higher, we have found that with increasing temperature from room temperature to 50 degrees Celsius temperature, there is a significant change in the flexibility. And we also have examined the tensile test for in underwater condition, and we have found with increasing the temperature from room temperature to 50 degrees Celsius temperature, SMG 70 SA30, the flexibility changes a lot. Here is the swelling properties of shape-memory-hydrogel materials, and we have found 60% of swelling degree for SMG 90 SA10 and 20% of swelling degree for SMG 70 SA30, where the crystalline concentration is higher. And this 40% difference actually enables the actuation. We also have observed the water uptake percentage and water release percentage. And you can see that most of the water uptake happened within 15 to 20 minutes. We have observed the temperature-dependent bilayer curvature formation, and we found that with increasing temperature, the actuation speed also increases. You can see in this condition where the thickness of the structure is 1 millimeter, length is 50 millimeter. At room temperature, it takes 120 minutes to form this coil formation, 360 structure. But if we increase the temperature from room temperature to 60 degrees Celsius, it takes only 0.37 minutes. We also observed the layer length dependent curvature formation, and we have found that longer the length, shorter the time for formation of coil shape. And for 20 millimeter length at 60 degrees Celsius, it takes 2.83 minutes. And for 40 millimeter at 60 degrees Celsius, it takes only 0.75 minutes. Here is the thickness dependent curvature formation. And we have found that with increasing the thickness, the formation, the actuation speed or bending time also increases. With increasing the thickness, the bending time also increases. This is the recovery process of the bilayer system, and in this process, I have used 50 degrees Celsius, 60 degrees Celsius, and 70 degrees Celsius. And we have found that at higher temperature, like in 70 degrees Celsius, the actuation or the recovery process is faster than 50 degrees Celsius and then 60 degrees Celsius. You can see in the video, this recovery is very slow at 50 degrees Celsius, but quite faster at 60 degrees Celsius and more faster at 70 degrees Celsius. Yeah. You can see this is much faster. In this section, I would like to talk about multi-directional single material 4D printing. For this system, I have used inter-crosslinking gel. We call it ICN gel. In this fabrication process, you can see this is the UV light source, and this is the glass plate and silicon spacer. And in this process, we don't need to change the material. With the single material, we can create the bilayer system. You can see we can create a white layer and a transparent layer. And when we put this structure into the water, it transforms. The actuation happens. In this technique, actually, we optimized the scan number and also scanning time. You can see here for 2 millimeter silicon spacer, for one scan, we can create this 2 millimeter transparent part, only the transparent part. And for 3 scan, we can create this white part, 2 millimeter. But if we use 5 millimeter spacer and we use 3 scan, then we can create approximately 3 millimeter white part and 2 millimeter transparent part. And this is the optimized technique for making the bilayer. And using this technique, we can create, as the beginning I have shown you the video of the box. This portion, you can create the purple portion, you can create using 3 scan. Here will be the approximately 3 millimeter white part and 2 millimeter transparent part. And this purple portion, you can use the similar technique. And for the hinge, you can use only 1 scan and you can create a 2 millimeter, approximately 2 millimeter thickness hinge. And for the scorpion, you can see the tail is going upside. So you can just flip the mold and you can print in the similar way. And for the hand, it moves sideways. And for this technique, you can use this this way to find this kind of actuation, like 3 scan. This is the upper view, 3 scan, and then 1 scan for this transparent part, and then 3 scan for the white part, and then you will get this type of actuation. So here is the summary of my presentation, that using SMGs, we were able to demonstrate swelling and temperature responsive 3D printed soft actuator. And our new 3D printing technique using ICN gels show the possibility of multi-directional single material based 4D printing. That's all. Thank you.